Thanks for the introduction. My name is Sinisa, and I'll give a talk today with the title of DelegateTEE, broker delegation using trusted execution environments and collaboration between 3 universities. So let me start with an example. Let me introduce Alice. She's an exemplary university student, but as all other students, she might be a bit poor, and so she doesn't have a bank account, she doesn't have a credit card account, she doesn't have a PayPal account. So she's really not able to do any online purchases very effectively. And then let me introduce Bob. Well, Bob is her dad, a businessman, wealthy businessman. He has all kinds of accounts, bank accounts, credit cards, PayPal. So what Bob really wants to do, he would like to allow his daughter Alice in order to buy some stuff online. However, he doesn't want to really give the full PayPal account. He would like to give her a restricted access to her account in terms of spending per month or specific stuff that she buys. So this is a simple example, and up to April this year, it was actually available by PayPal. It was enabled by PayPal itself. So basically, you could have a student PayPal account where the parents can give you some access, restricted access to the account itself, so you can spend some money. However, PayPal dropped the support for this, and there's really no indication if that's going to be introduced again. So there's a problem here. So Bob would really like to make his daughter Alice happy. However, he's fine sharing his account. Absolutely, why not, But he doesn't really want to give her username and password, the full login credentials, because that would also give her unlimited spending capabilities. And as well, Bob is super security aware like all the other people, and he uses the same password on all of his online services. So what can we do there? So if the service would actually allow this, why different online services wouldn't actually allow some sort of restricted access that can be given to other users? And this is not only applicable for PayPal, this is just a motivating example, but we can see that in all types of online services that are behind some kind of password authentication. So delegation itself is only possible if directly supported by the service provider, and basically the service provider dictates the terms of such a scheme. So for example, Facebook allows some sort of delegation, but however, it's mandated that, if you give rights to a specific app that it can post something, you can't really dictate what that app is going to post, or it's going to be 3 times a week, or at what hours, and etc. So a solution to this general problem could be broker delegation. So let's go back again to the example. We have Bob, and we have a service, and Bob has access to that service. And then on the other side, we have Alice, but Alice doesn't have access to the service. So a solution to that would be that if we have some kind of a proxy that can lie either in the middle, somewhere in the cloud, or some kind of a proxy that lies on the Alice's side, which can allow us actually for Bob to deliver credentials to that proxy, and then Alice could actually access the service through it. So the key point takeaway here would be that this proxy, of course, needs to be trusted, because you would need to offload some of the secret material inside of it. And that brings us back to the title of the talk. So broker delegation using trusted execution environments. So I'll briefly explain a little bit about trusted execution environments. So modern TE environments, and this is most notably known, are ARM Trust Zone and Intel SGX, enable isolated code execution within a user's systems. Unlike Trust Zone, which actually permits execution of the code in some kind of a secure world, which indicates a complete context switch from the normal world to the secure world on phones, Intel SGX has a different kind of setting where you have secure enclaves running with user privileges on the side. So how it actually works, you have a secure enclave that is running a trusted part of the code, and you have an untrusted part on the outside that actually dictates the execution. So what SGX, and this work is based on Intel SGX, but gives us is runtime isolation, as we said. We have the eCall and OCall interfaces, which actually give us access to the outside OS untrusted part and back in. Sealing as a term that allows the enclaves to store stuff on the encrypted on the main disk storage. And maybe the most important thing is attestation. And what attestation gives us is actually the ability to verify that a certain piece of code is running inside of a secure environment, such as a secure enclave in Intel SGX. Also, the memory content of these secure enclaves is encrypted, and this is, of course, important for confidentiality of data as well. I don't know if any of you listened to talks yesterday, but yesterday we had a complete session on side channel attacks. So trusted execution environments are vulnerable to some kind of attacks, most notably side channel attacks. We've heard about Spectre, Meltdown, and Foreshadow that actually break the guarantees that such systems like SGX gives. However, patches are on the way, and it's the point of this talk and this work is not actually to talk about the security of trusted execution environments, but to see how these elements could be used to create new stuff, new markets, new ideas, etc. So basically, if we go back to the title of the talk, so we do the broken delegation with the enclaves. It's a concept of delegation is familiar also in the computer science and in general in life, and it sounds very familiar. But what broker delegation with enclaves gives us is that it allows us to flexibly, securely, and selectively share and delegate access. So this can be access rights, credentials, anything that you own, you can delegate to a third party or another user. What is really important here, and that also makes one of the main distinctions from all other delegation schemes, is that no explicit support or even knowledge is needed on the service provider side, which you use actually these services to delegate to other people. Broker delegation with enclaves allows us actually to create fine-grained delegation without the trust between the credential owners and third parties that are getting the rights by defining rich access control policies that can be applied to almost any online service and any protocol out there. Of course, as I said, this is supported with the usage of TEs because we use them as the main building block that actually allows us to do this stuff. We distinguish, and I'll distinguish these two parties in the rest of the talk. So we have the credentialed owners that give access, and we have the delegatees that receive the restricted access. So what are the challenges and desired properties that we would like to have in such a system? First and foremost, the owner's credentials should always remain confidential, and they should never be revealed to the delegatee who receives access. Second, the owner should be able to restrict access to his accounts, and this should be done depending on the type of online service that we are talking about. So it should be some kind of a rich contextual policy that includes terms of usage time, duration, read, writes, really depends on the service that we're talking about. The system that supports this should also be able to actually log different activities and actions done by the delegatee in order to, as kind of means of resolving disputes if the delegatee actually does some harm using an owner's account. Second, more to it is that the system itself, so the service provider, should not be able to actually distinguish from the usage patterns, is it the real credential owner or the current user of the system is somebody with a delegated access. And lastly, we don't want the owner to be always online. So we don't want the owner itself to be the proxy of such a connection. So we want an owner to give access rights, give credentials, and actually then connect, disconnect, and then continue. So we developed two main architectures, and a peer-to-peer system model as explained in the solution slide, where actually the proxy resides on the platform where the delegatee sits, in a centrally brokered system. For the ease of explanation, so these two systems are interoperable. It's actually the same system which you can deploy either on the cloud or you can deploy it on a local machine, but we'll focus more on the centrally brokered system. So to give you a bit of a glimpse how it works, I'd like to quickly walk you through the design of the protocol, high-level design of the protocol and involved parties. So as we said, we have owners on one side and we have delegatees on the other side. And then we have services on the third side. In the middle, we have a centrally brokered system. So how the system actually operates is that first the owner and the delegatees need to register with the system. They're like a normal online registration to any other service. You get a username and password, and that's it. Second, the owner needs to establish a secure communication. So that's what this really means is this is a really important part. The owner needs to do an attestation of the system to really see that the code running on the centrally brokered system is what it's supposed to be or what it claims to be, and that it doesn't have any malicious part in it. After that, the owner can store credentials of his online services to the system, and that's it. Now, if the owner and the delegatee know each other, they can use any informal communication channel to actually exchange relationships and say, I want to delegate you my account for this, I want to delegate an account for that, and these are going to be the rules. And after that, they exchange the unique identifiers for the system, and then actually the owner can create a delegation relationship, which actually means, saying, please delegate these credentials to this service, to this specific delegatee under this access control policy. And that's it. The owner can disconnect and he can go on. The delegatee can now connect to the system and actually establish a secure communication the same way, which then gives him the availability of the delegated access to a service. The access to the service is always given through the proxy, so there is never a direct connection between the delegatee and the service. It always runs through the centrally brokered system, so you can envision it as a kind of a man in the middle. And if everything is, the delegatee has access until everything is filtered, until everything is okay with the access control policy, because it gets filtered on the centrally brokered system. Once the policy expires or the actions are not according to policy, the access is cancelled. So basically, what are the trust assumptions that we have here? We trust the enclaves for confidentiality and attestation in order to fully protect the owner of the system. The server and the operator of such a system don't actually per se need to be trusted, because we put the trust inside of the enclave, so the operating system can be completely untrusted of what happens. This we achieve by using end-to-end TLS connections, so from the enclaves to the users, either owners or delegatees, or from the enclave to the service operator. So we developed several case studies, so full implementations of this system for several use cases, and I'll present a couple of them right now to show you the potential of that. So let's go back to the PayPal example. We have Bob, we have Alice, we have the merchant, and then we have the PayPal as the payment provider, and then we have a centrally brokered system in between. So what happens is that Bob delivers the credentials to the system and specifies to whom he wants to delegate, and also alongside that the restrictions. Alice goes to a web shop, chooses what she wants to buy, and actually when it's time for payment on checkout, she actually doesn't choose a normal PayPal, but she actually chooses to pay with DelegateTEE in this case. So what that actually happens, she needs to be logged in to our system. The system performs checks and actually hijacks the session from Alice in this case, and actually performs the payment directly with the delegated credentials saved from Bob. What happens after the payment went through? Alice is forwarded to the landing site confirming her transaction. So I'll show you how actually the demo, I can demo because it would take a lot of time, but I'll show you the screenshots of the demo. So it's a normal web shop, it's a Swiss web shop. We put some we put some items in the cart. We chose PayPal as the payment option. We click Pay, and this actually takes us to the PayPal site. What actually happens here is that there's a browser extension that renders the page and searches for fill-in forms. It identifies a PayPal login button and then inserts another button below. So now you can click on that button and you get a pop-up. And the pop-up from the extension actually gives you the ability to choose if you have any of the delegated credentials which you want to use to pay. And in this case, we choose Andrew's PayPal, we press execute payment. What happens here is that PayPal doesn't really only rely on that, but they have another security mechanism of a CAPTCHA. So actually the system intercepts the CAPTCHA, presents it also through a pop-up in the browser extension to DelegateTEE. DelegateTEE can fill in the CAPTCHA and submit the payment. In the end, that's it. The payment went through and an item was purchased. So I'll give you another example. The other example where this works and where this was implemented is also the credit card. So when the system registers there's a credit card form on the site, it also inserts a button, and basically when you click on a button you can choose to pay with this delegated credit card. Another thing which is important here is that the system does not fill in the form on the website, so it doesn't ever reveal the credit card number itself, but it actually performs the payment directly. So it fills in the form and sends it directly to the payment provider, whoever does the online payment online. Another implemented example that we did is email. So imagine you want to delegate access to your email to your personal assistant, but you really don't want him or her to see emails from your wife or from any other friends or whatsoever. So you can delegate access to the email by actually just specifying that that person can read emails or get emails or send emails or do anything with the emails only, if they match a regular expression or if they're concerned about a specific domain or anything. So in the case of email, the power is really, the power of what you can do is really strong because the protocol is standardized. So you can really filter all the incoming and outgoing traffic and allow or disallow certain actions. Last but not least, this can be used as a general website browsing or any other account control, admin system, CRM, anything that uses HTTPS and that uses password authentication. So basically also when you see a username and password fill-in form, you can get this button, you can click login with DelegateTEE, you can log in with the system and have another type of restricted access. Basically what this deep down is, it's an HTTPS proxy, a secure HTTPS proxy that's running inside of SGX enclaves, and now it depends on the policies and protocols running through it, what you can actually do with it. Just to go quickly through the performance, so the performance is in line with the original performance of the use case scenarios, so the deviation of the performance of a specific service operator is greater than the overhead that we have here. In terms of a peer-to-peer system, you don't even feel any overhead because the actual proxy is residing on your machine. When it comes to the centrally brokered system, of course, it needs to go through a cloud environment for you to actually get traffic. So the only difference between these two is that in a centrally brokered system, you can't really log into a service like Netflix and stream video, because if that would be done by 1,000 users concurrently, there would be a heavy overload and a heavy bandwidth on the centrally brokered system. While in a peer-to-peer, where it's one-to-one delegation relationships, you can do that. So this is all nice. These are all nice examples, but actually what this scheme or broker delegation might do is that it may undermine services policy enforcement. And it's a very simple thing to explain. So this is basically, you can transform any mandatory access control to a discretionary access control. So this is similar to something like set UID on Unix systems. So if you have an access to any online system and the enforcement is mandated by the service operator, you can simply give your rights, restricted rights, to a third person under your full control and under your restrictions. So where this might come as a thing not liked by the service operators is that you can start building secondary markets for almost any service. So Netflix, I don't know how many of you have Netflix, but I guess if you buy a subscription on Netflix, a 4K one, you can watch it on 4 devices simultaneously at the same time. None of us do it on 4 devices at the same time. So why wouldn't I watch Netflix on my phone, and why wouldn't I resell the 3 other subscriptions that I have of my Netflix? I mean, that sounds nice, but wouldn't probably be accepted that well from Netflix, because Netflix also doesn't do geofencing. So you can, have one account in the US, have one in Europe, have a third in Asia watching at the same time. It's allowed by Netflix. But what really these service operators rely on is that you won't share your credentials that easily. You will do it only in your close family and friends. You will never put your username and password somewhere, because of course your credit card is inside, and then maybe some of your identifiable information. Another example could be that you have a paid subscription service, almost anything, so it's news portals, anything that is behind a paywall and password authentication, and that's it. So as I said, basically services are the ones that expect the difficulty of sharing this. So they're really not concerned about that, because if you don't have a secure system where you can offload the credentials, it's very difficult to do that. I'm a bit over time now, so of course there's a lot of discussions and challenges and limitations about this scheme and model to present. I would encourage you to, if you're interested, to see more details about different models of deployment, how policies could be created and enforced, and also about authentication challenges, what can be done there. If you have two-factor authentication, such things like CAPTCHA, what about authentication collisions, usability deployment, what about if the service wants to prevent the usage of such a system, scalability, and so forth. And to shortly summarize, so the broker delegation actually gives us secure and flexible delegation of user access and rights, applicable for online transactions with password authentication. No changes are needed on the service side. Compatibility is with a wide range of services. Of course, some of them need to be explicitly developed, like we explicitly developed these 4 use cases scenarios. It's implementation heavy. It can give rise of new sharing economies and business models. And the last question is, this could be a potential game changer. So the market disruptor. So we imagine that in the future world, where remote attested enclaves would be acceptable, not like yesterday, because I guess after yesterday nobody wants to use SGX anymore. But after we patch things up a little bit and we move on, all the systems get broken eventually. So this would be a very appealing thing to do, not only for the use cases presented here, but it's an open-ended game. If it catches on, service providers will either have to go with it, catch the market themselves, or really switch the authentication not just to be simple passwords or simple protocols that we can circumvent with the system. Thanks. Any questions?
Any questions?
Hey, great talk. I got a quick question on how you envision managing all these devices and at the attestation portion. It seems like you're sort of expecting the central broker to know all the software that should be on the system, and in a P2P peer-to-peer model, it might be even more challenging to know what kind of software I should expect to be good on the target system. If I'm negotiating with someone's iPhone or Android device, I don't know if something's malicious or something might take control, because it looked like what you were saying is you can securely get all of the credentials all the way from the web browser stack from the input all the way down into the enclave and then out.
Yeah.
So it's that's sort of an interesting challenge that I don't know if you thought about.
Okay, I'll try to answer your question. So basically, if this is community developed, then you will have a software package that could be running in an enclave. It should have some kind of hash so you can verify which code it is. It will have a signature that you can verify where from this code have came. And then in that case, if you attest that part of the code, then you can compare it to a publicly reliable source or a company that is running the service. So it peer-reviewed, like just online, having it to GitHub, then the community will tear it apart if something's wrong with it. Of course, there are specific cases if it's running on a security-related things, if it's running on a machine local proxy, and if it's running in a centrally brokered system, because it might be more difficult to break a centrally brokered system because it's in the cloud, so it has other security enforcement, while if it's on a machine of a specific person, then, well, yesterday talks happen, and then you can use the credentials.
Hi, John Criswell, University of Rochester. So a completely non-technical question. So essentially what you're doing is you're providing a new service or new services on top of existing services. So if these new services become popular, what keeps the original service provider from just providing them? And if nothing, then doesn't that kind of cut out the marketability of the additional services being bolted on with your technique?
So actually nothing prevents them of doing it. That was the motivating example. PayPal was doing it. The question is why they're not doing it. Why is Netflix selling you 4 accounts for $10.99? Why is it not selling you one for $2.59? Why? Because you'll buy the 4, 3 you won't use, but you'll still pay 10. So yes, of course, the reaction of the service providers can be that they react to this and then they try to grab the same market. But that's also going to disrupt them because their revenue is going to go down. They will have to change their business models. And it's not really easy to change a business model that is already operating and is generating revenue. So that would be great. If all of the services would allow this, that would be awesome. But they don't. And they never will. There's no service where I can use other people's PayPal accounts or credit cards to buy stuff in a restricted manner where I can set the policy, only this web shop, only this item, up to this amount of money per day, per month, after midnight. You can really do whatever you want. And there's no service that actually allows you to create that kind of rich contextual access control policy and give restricted access, unless it's some kind of enterprise system for a specific use. And this is general.
I see. Thank you.
So would there be any legal implications too? I imagine some.
Absolutely.
Right. So
that's the point.
Well, I suppose for Netflix.
No, I'm joking. So I mean, of course, by using the service, by using the system with a lot of different service operators, you will break terms of use. That's the point. I mean, you can't really avoid that. But whoever, I don't know who reads terms of use,
All right, let's thank the speaker again.
Thanks.